welcome back to the explainer. You know, if you've ever Googled the word recursion, you've probably seen that joke where Google asks, "Did you mean recursion?" Right? It's a notoriously mind-bending topic. But here's the thing. If you understand how basic function execution works, you've already got everything you need to master this. We're going to strip away all that confusion today and look at the exact mechanical reality of what happens when code literally loops into itself. Okay, let's look at our roadmap. We're going to hit what is recursion, the infinite trap, understanding Stack Overflow, the base condition rescue, and finally, the recursion tree. Let's dive right in.
Section 1. What is recursion? Let's quickly break down the anatomy of a recursive function.
Read this definition carefully. It's kind of like a set of Russian nesting dolls. There are two absolutely mandatory parts here. First, the self-calling action. That's opening a doll to find another one inside. And second, the vital stopping point. That's the final solid doll right at the center. Calling the function initiates the loop, but if you just do that first part without hitting a stopping point, well, that's a total recipe for system failure.
Which brings us to part 2, the infinite trap. Let's look at what happens in your computer's memory when a function literally forgets to stop.
Imagine you've got a super simple function, let's just call it f. Your main program runs it. Inside f, it prints the number 1 to the screen. Pretty easy, right? But immediately after printing, the very next line calls a replica of f again. And because the function is actively open in your memory, it jumps right back up to the top, prints 1 again, and hits that call again. It's basically a localized Groundhog Day for your processor.
So when does it stop? Well, that's the million-dollar question. With no condition telling it to halt, you've just built an infinite recursion. Your screen turns into this endless scrolling blur of ones. This is exactly what's going on under the hood when a piece of software completely locks up on you. There's just no instruction telling the processor to break the cycle.
Moving on to part 3, understanding Stack Overflow. What's physically happening inside your hardware when we trigger this infinite trap? Think about the waiting game that's happening here. When that first function calls the second one, it's not actually finished yet. It gets pushed into a designated memory area called the stack space. Imagine putting a dirty plate on a physical stack in a busy restaurant kitchen. Then the second function calls the third, throwing another incomplete plate onto the pile. Since no single function can finish its final line before calling the next one, these incomplete tasks just pile up, waiting, getting higher and higher. But your hardware has physical limits, right? If you let this run, the music eventually stops. Depending on your compiler, the program might crash after some arbitrarily high number, like say exactly 523,037 calls. You literally run out of physical memory. The computer just cannot juggle tens of thousands of uncompleted waiting functions forever. And when it hits that absolute physical limit, boom, it throws a segmentation fault. This total memory crash is universally known among developers as a Stack Overflow. And yeah, it's the exact same Stack Overflow you probably visit to desperately search for coding answers. The memory stack quite literally overflows its boundary and just kills the program. All right, part 4, the base condition rescue. How do we pull off that second half of the definition to successfully stop this loop? The answer is the base condition. Think of it as your program's emergency brake. Imagine we have a global variable called count, starting at 0. Right at the top of our function, we drop in an if statement. We're asking, hey, does the count equal 3? If not, we print, bump the count up by 1, and recurse. But if it does equal 3, we hit it with a return. That return is a hard command that says, okay, terminate right now.
This is literally the line between chaos and order. On one side, infinite recursion is blindly piling up uncompleted functions until your entire system bursts. But on the other hand, the base condition acts as this incredible rescue shield. By mandating a hard stop at count 3, it actively kills that forward momentum. It finally allows all those waiting functions stuck in the stack to breathe, execute, and resolve. Let's trace how this rescue actually plays out. Count 1, count 2, count 3. The exact moment that condition is met, the return triggers. That active function immediately terminates, and because it's finally done, the function directly below it, the one that's been waiting in the stack all this time, can finally execute its last line. Then it finishes. It sets off this rapid upward chain reaction, safely popping every waiting function right out of memory until you're cleanly back in your main program.
Finally, part 5, the recursion tree. How do we map this whole life cycle out without getting totally lost in the weeds? Look, when you're engineering complex software or sweating it out at a whiteboard during a technical interview, you can't just write out massive blocks of duplicate code to show your logic. So we use a recursion tree. It's essentially a truncated blueprint. We replace all those lines of code with simple nodes, mapping out exactly who calls who and, crucially, where those returns actually happen.
This tree shows you the exact journey at a single glance. The first function calls the second. We dive down a level. The second calls the third. Then, right at the bottom branch, the base condition strikes. And now we trace it all back up. The third returns up to the second returns up to the first, and the first safely delivers you right back up the chain to your main code. Recursion is honestly a developer superpower. Left unchecked, it will ruthlessly crash your system's memory, for sure. But when you harness it with a precise base condition, it becomes one of the most elegant tools you can possibly use in programming. Now that you understand the invisible mechanics of the stack space and that upward chain reaction, you are ready to tackle far more advanced data structures. So I'm going to leave you with this to think about. What complex, seemingly impossible algorithmic problems are you going to solve now that you know how to master the infinite loop? Keep exploring, and I'll catch you in the next explainer.